Hi, as I was just introduced, my name is Sally Longmore, PhD candidate for the Marks Institute for Brain Behaviour and Development at Western Sydney University. I had a previous career of 18 years in information technology before I decided to go to university. When I was younger, I didn't really have, couldn't really afford to go to university at the time. So it wasn't something I really considered when I was younger. However, after working in information technology for 18 years, I sort of got a bit bored of working in that field and needed something different to stimulate my mind. So I went to university and studied at Western Sydney University a Bachelor of Medical Science Advanced, which I'm proud to say I graduated with distinction. Then I went to do a master's at Western Sydney University, which has been upgraded to a PhD after the work I did in the first year of my PhD degree. So that's a little bit of my background. I'm also a passionate advocate for renewable energy and electric vehicles. Particularly through my research, I've found that our transition to zero emissions is not only critical for climate change, but also critical for human health, as we'll see in today's presentation. So myself, I'm not just talking about it, I am doing it. We have a 9.6 kilowatt solar system at home and 2 Tesla batteries to power our house. And we only have electric vehicles, so we don't have internal combustion vehicles. So I'm not just talking about it, I actually live it as well. So let's move on. So let's start with this number, 8 million deaths. So the World Health Organization estimates that there is 8 million deaths a year as the result of the exposure to air pollution annually across the world. And this figure includes outdoor air pollution as well as indoor air pollution, which, although I'm not really talking much about indoor air pollution today, it is a health hazard. It's particularly not so much in Western countries where we tend to have either gas or electric and tend to have ways of extracting that out of the house. So it's not quite so bad, but particularly in third world countries where they cook using open wood fires or even dung from animals. So out of this 8 million deaths, we have 4.2 million deaths from outdoor air pollution each year. And we'll look at the sources of this outdoor air pollution shortly. But first, let's put this number into context. That's 54 deaths per 100,000 people worldwide each year will die from association to air pollution. But let's look at this in relation to COVID-19. Now, obviously, COVID-19 is a horrible virus. It's impacted a lot of people worldwide. But when we look at the figures for COVID-19 to date, we can look at a number of 12 people per 100,000 people have died from over this year from COVID-19. That's assuming that the death rate continues at the same rate throughout this year. But air pollution is going to kill approximately 54 people per 100,000. If we put that back into our number of people per year, that's 4.2 million people who are going to die from air pollution this year, and 950,000 who will die from COVID-19. So while it's horrible that we have such a death rate from COVID-19, and many of these deaths are preventable through the actions we have taken, and we've shown that in Australia, that if we band together, we can do something to prevent these deaths. However, as a society, we do relatively little to combat the 4.2 million preventable deaths from air pollution. We have the technology today, renewable energy production and zero emission vehicles to actually do something to prevent these deaths. But we don't have the political will or the society will to do so. And considering we did something about COVID-19, I think it's a real miss that we're not doing something about air pollution. We're not doing enough to prevent these air pollution related deaths. So what's in the air? Well, It all started really about the Industrial Revolution in the early 1700s with the invention of the steam engine. So the steam engines would run on either wood or coal, and what they would do is they basically powered factories using steam. And because the factories were located in centralized factories like in cities, because previous to the Industrial Revolution, it was mainly farming and hand production of goods at home and small businesses who didn't use energy resources such as that. Yes, they'd use fire and stuff, but not in the scale that the Industrial Revolution brought in. But it was all centralized to the factories and cities. So these factories were powered predominantly by steam engines that would turn machinery, allowing large-scale production of goods not seen before in human history. And that really spurred human civilizations to move forward. However, over a relatively short time span, on the scale of human existence anyway, we have decreased the air quality to such an extent that the air can now kill us, which is not something we saw before the Industrial Revolution. Not only has it affected us, however, I should be on this slide, not only has it affected us, however, it's also affected the evolution of other species. We've seen mass extinctions across the planet. We're seeing climate change because of this, but we've also seen stuff like the peppered moth in the United Kingdom, for example. The peppered moth, it comes in two colours, or two shades, I should say, a light shade and a darker shade. Before the Industrial Revolution, the light shade was predominant, as it could more easily camouflage into black trees, or the bark of trees. However, soot from coal-powered steam engines rapidly blackened tree trunks. And this meant that the light-coloured pepper moth was no longer fit for new coal-polluted environment and was predominantly eaten by birds compared to its darker brethren. And therefore, the darker moth began to dominate. So not only is it affecting humans, but it's also affecting the evolution of species and also causing some species to become extinct. So what's changed? Well, a lot has changed since probably about the mid of this century, of the 19th or 20th century, I should say. We've moved a lot of coal burning energy sources outside of major cities. And this has effectively moved these pollution sources somewhere else. They still pollute, however. We have generally made cleaner fossil fuel powered motor vehicles. They're a lot cleaner than they were, even 20 years ago. However, we have a lot more of them, particularly in countries which never had them before, such as China. They had a very small density of motor vehicles, but nowadays they have a very high density of motor vehicles. And another country with a similar situation is India. So although we have cleaner vehicles, we now negated any gains from those cleaner vehicles through a lot more vehicles on the road. And most of these vehicles are located in densely populated cities. So the improvements from moving from coal power out of cities has largely been negated by the increased internal combustion motor vehicles.
So I got 4 things: potatoes, eggplant, quick cook oats, and
so anthropogenic climate change.
potatoes, eggplant, quick cook oats, toilet.
So of course we also know that the process that produced air pollution also contributed to anthropogenic climate change. The combustion of fossil fuels used today to power our society also generates large amounts of carbon dioxide, which fuels climate change. These changes from burning fossil fuels on climate change are felt over decades. But we are seeing those effects today now from worsening bushfire seasons, higher temperatures, worsening storms, and more frequent droughts. Unfortunately, policy on reducing emissions with regards to climate change has been slow. However, the effects of air pollution on human health are more immediate with disease and death. But both climate change and most air pollution share the same, air pollution caused disease and death share the same common source, burning of fossil fuels for energy and transportation. So if we solve one, we solve the other. Since air pollution's effects on human health occur on a much shorter timescale compared to anthropogenic climate change, solving air pollution may have a more immediate effect on governments' health budgets and therefore may have more traction in policy change with regards to fossil fuels. Therefore, research into the effects of air pollution on human health and physiology is important. So let's look at the causes of air pollution. So as we could see in the background of this photo here, which was taken from Wattle Grove in 2018 when there was a huge bushfire there, bushfires are a major cause of natural cause of air pollution, as are dust storms and pollen. However, while bushfires and dust storms can occur due to natural weather phenomena and natural climatic changes, they can also be triggered and exacerbated through human causes, such as deliberately lighting fires and climate change. While not the primary interest in our research, natural causes of air pollution such as bushfires have become a side research project for us, particularly after the 2019-2020 bushfire season. So let's have a look at the human causes of air pollution. Human causes of air pollution primarily are caused through fossil fuel combustion. Electricity production through coal and gas-fired power generation is a significant contributor to air pollution. However, it is often more located outside city centres and metropolitan areas. In cities and major metropolitan areas, traffic-related air pollution, or TRAP, is a major contributor to air pollution. Exhaust gases from combustion of fossil fuels in motor vehicles include nitrogen, carbon dioxide, water vapour, carbon monoxide, nitrogen oxides, sulfur dioxide, and of course, particulate matter. So of particular concern to human health is the particulate matter component of motor vehicle exhaust. Therefore, particulate matter is a main interest in our research on the effects of pollution on human physiology. Air pollution and disease. Throughout the literature, air pollution has been associated with a range of different diseases. These include things like respiratory disease and cardiovascular disease, and they're quite the first thing most people think about when air pollution and disease are talked about, because they're the two primary interfaces with the outside environment or the air. Stroke is another one. And we've also seen associations now with dementia, low birth weight and premature birth, and many different types of cancers. And so let's look at air pollution and respiratory disease. So our lungs are the primary interface between the air we need to live and our internal physiology. As such, they are most commonly affected by contaminants in the air we breathe. Gases can easily diffuse across the alveoli into the bloodstream. However, that is not necessarily the case for particulate matter. Coarse particulate matter, generally defined as PM10 or less than 10 micrograms, tends to get trapped by the mucociliary pathway and expelled by the body in mucus, which is good, it comes out. These coarse particles, however, can cause irritation of the airways and then cause coughing and breathing difficulty, particularly in individuals who suffer from respiratory diseases such as COPD or asthma. They can also become lodged in the lungs and cause cancer. However, what is of more concern is the finer particulate matter particles. They are more dangerous. Particulate matter less than 2.5 micro.
So I'm trying to do the right thing and listen.
Sorry, I thought someone was asking something. Particularly very fine, so particulate matter less than 2.5 micrometers in diameter are a high concern for human health. Particularly very fine particulate matter less than 1 micrometer in diameter. And then you've got the ultra-fine particulate matter, which is less than 0.1 micrometers in diameter. That's of a real concern. Particulates of these sizes can cross into the bloodstream via the alveoli in the lungs and then start to affect other bodily systems. So within the respiratory system, however, air pollution has been associated with the development of pediatric and adult asthma, chronic obstructive pulmonary disease, which is COPD, which I mentioned earlier, and also lung cancer. It can also be associated with the exacerbation of symptoms of these diseases requiring medical attention and hospitalization. In severe instances, air pollution combined with chronic respiratory diseases can be attributed to the death of patients. In a letter to the Medical Journal of Australia by, I'm going to murder this name and I do apologize, Ariganda et al. In 2020, they estimated the air pollution from bushfires were associated with 417 deaths across Eastern Australia. And that's the 2020 or 2019-2020 bushfires. It was also associated with 1,024 cardiovascular hospitalizations and 2,027 respiratory admissions and 1,035 presentations for asthma. So sadly, these figures aren't really seen when the bushfires exist. It's something it comes about through research afterwards and really needs to be counted in the figures for the deaths for bushfires and also the hospitalizations and disease caused from bushfire. Air pollution and cardiovascular disease. So once the pollutants such as fine particulate matter have crossed into the bloodstream, they can then cause disease in other systems in the human body, such as cardiovascular disease. Cardiovascular disease is the largest cause of mortality globally. It has many different causes, however. Air pollution has been recognized as a risk for cardiovascular disease. Cardiovascular diseases associated with air pollution include heart disease, diseases of the blood vessels, and stroke. So let's have a look at air pollution and disease studies. So throughout the literature, air pollution and its relationship with disease has been studied in both cross-sectional studies and controlled crossover trials most of the time. There is some others, but most of the studies are those types. These studies have shown a strong association between exposure to air pollution and the development of disease. Additionally, some of these studies have shown a relationship between the short-term exposure to air pollution and acute physiological symptoms. And these can go on to then cause things like asthma attacks and instances where people with respiratory and cardiovascular disease need to go to hospital for medical attention. I'm not great with pronouncing names, so I do apologize to these people beforehand. Niseki et al. In 2016 conducted a cross-sectional study of patients with chronic obstructive pulmonary disease with respect to traffic-related air pollution near the homes of patients in Adelaide. It was found in this study that patients with COPD or chronic obstructive pulmonary disease whose homes were located near high traffic density roads generally had decreased lung function compared to patients who live in lower traffic density areas. A similar outcome was seen in healthy patients, but not to the same extent. However, in a controlled crossover trial by Sinray et al. 2020, participants were asked to walk on a busy street in London and 3 to 8 weeks later, walk in Hyde Park. They found that the participants with COPD and ischemic heart disease walking in a low pollution environment had better respiratory and cardiovascular responses compared to when they walked in high pollution environments. However, they also found that it wasn't so clear cut when it came to healthy individuals in those tests. So some of the issues with these studies. So there's some issues with the existing studies into air pollution and disease and human physiology. And these are that they tend to have a low geographical resolution of the environmental data, which is insufficient to identify an individual's exposure to pollutants. So what I'm saying there is it's very hard to identify an individual's exposure and put that to an outcome. We can only generalize that exposure because we don't have the sensors on the individual. They can be located up to 15, 20 kilometers away from the individual in these studies. For example, in the study by Niseki et al., the pollutant exposure for patients in Adelaide was estimated based on the proximity to main roads. So it wasn't really a direct measurement of the pollutant in that area, rather a proxy was used, i.e. the proximity to main roads. While in the study by Sinray et al. In London, air quality measurements were taken from fixed ground-based monitoring stations, meaning that the actual exposure may be different for each participant. And I'll explain why that's important a little later on. Also, most studies have insufficient temporal resolution of the environmental data for researching acute changes in physiology. Either they use a single point in time, or, as in the case of the study in Adelaide, or an average reading over time, as in the case in the London one. So I got them back to front, sorry. The London one was a single point in time. The Adelaide one was a sort of like an average over time. Additionally, these studies have low temporal resolution of physiological data. Often a single point in time is measured, such as a visit to a hospital, an ambulance call out, or a death record. All the physiological data is collected at intervals from, say, 30 minutes to hours. In the study by Sinray et al. In London, participants were measured over a long period of time. I think it was like 24 hours or something like that. I can't remember the exact number off the top of my head. However, the frequency of measurements was between 1 and several hours. So the frequency changed over the study period. It wasn't at set frequency intervals, but the minimum frequency interval was 1 hour, and it went up from there. So this means we can't really look at the acute changes of human physiology with respect to the changes in air pollution, because we can't see it at that resolution of data in these studies. So what are we doing differently? Well, an important point we need to make is that air pollution can vary significantly in as little as a metre from the pollutant source, particularly near main roads. In a study by Sharma and Kumar in 2018, they studied what happens, the difference between a parent who's pushing a baby in a pram near a road and the baby in the pram, and the difference of exposure to air pollution between the two. And what they found is that the exposure the exposure to the air pollutant from the baby was significantly higher than that to the parent. And the parent's mouth may only be a metre away from the baby's mouth, and the baby was a lot lower to the ground. So that's the one reason why we need to have better geographical resolution of the data, particularly when you're looking at acute studies. You want to have that data from the actual person, particularly as close to the human head as possible. So therefore, we set out to measure the microenvironment of our participants. So what we're doing is we're placing the environmental sensors as close as possible to the participant's mouth and nose while not impeding their day-to-day activities. We also have increased the temporal resolution of the environmental data from hourly averages found in many other studies to data collected at 5-second intervals. So we can see that change pretty much in real time. And that may change as a truck drives past, for example, or wind direction changes. So it's important that we collect that data, especially when we're looking at acute changes to physiology at a high temporal resolution. Additionally, we will have a much higher temporal resolution of physiological data. The physiological data we'll collect will be at 1 Hertz, which is 1,000 times per second throughout the entire experiment, rather than at fixed points in time. So from the time the experiment starts to the time we end the experiment, we'll be collecting that data constantly at 1 Hertz. This will enable us to see acute changes in physiology with associated changes in air pollution exposure in real time. We expect this will reveal any lag between exposure and physiological symptoms, exposure to air pollution and physiological symptoms. So our hypothesis. So we hypothesize that an acute increase in heart rate variability, and respiration rate with an associated decrease in blood oxygen saturation will be observed when test subjects are exposed to environments exhibiting poor air quality. Further, we hypothesize that in individuals with a history of respiratory disease, such as asthma, the associated response to exposure to poor air quality will be higher than in individuals with no previous history of respiratory disease. So, how are we going to do this? Well, this is our WEBS platform. So, WEBS is our wearable environmental and biological sensor platform. It shares the same base hardware as the Citizens Science Environmental Sensor Stack, which we'll talk about shortly. It can use Bluetooth and Wi-Fi connections to connect to the internet and upload data directly to servers, or to a phone, a mobile phone, so it can connect to a mobile phone or home Wi-Fi. And we can also have an app showing that data to the participant as well. It's got a micro SD card for local data storage, so we can store the data locally as a backup. And as I said, yes, we've got a mobile phone application as well. So the test participant can actually see that data. We can, if we wanted to have an extended test, say over several days, we can even have alerts go to that test participant to say, hey, you're in a really dangerous area with regards to air pollution, maybe you should seek shelter. The environmental sensors include a particulate matter sensor, and the particulate matter sensor can measure PM10, PM4, PM2.5, and PM1.0. Now, I will talk more about what PM means shortly. Gas sensors, so we've got nitrogen dioxide sensors, but we can extend the platform to measure other gases. For example, we could add carbon monoxide sensors, we could add sulfur dioxide, and we could add carbon monoxide. Volatile organic compounds is another measurement that our device can take, as well as temperature, pressure, and relative humidity. And they are sort of important as well, because the respiratory rate and heart rate can change depending on temperature. Physiological sensors included in the platform are a photophlesmography sensor, or plethmography sensor. I always struggle with that word. I'm going to call it PPG from now on. So if you hear me say PPG, that's what I'm referring to. And this sensor is a really good sensor, and we'll talk more about this sensor shortly, but it can measure heart rate, respiration rate, and blood oxygen saturation, as well as heart rate variability as well. We're going to have a body temperature sensor, which is against the forehead, accelerometer in there as well. That's going to help us with any movement artifacts, and a global positioning system, so we can keep track of where these measurements are being taken. Okay, don't know why I put that slide in twice. And basically this is what it looks like. So it's all going to be head mounted. Now, the reason we wanted it on a hat and head mounted like this is it doesn't impede the test participant or the person using the device in any way. They can go about their normal day. It's not like if we had the sensors on the finger, then obviously, you know, it's going to be difficult to type or do other tasks with your hand. We can't monitor the patient or the test participant continuously. So we basically wanted to make it so that the test participant can go about their normal daily routine with minimal impedance from our test platform. And so all the sensors are built into this hat, including the batteries and everything. The only thing that's not is the mobile phone, and that's what's used to transmit data back to the server. So let's have a look at what we've done so far in our existing research. So one of the first projects we did was tested the PPG sensor location on the body, because we needed to make sure that the PPG sensor would work effectively on the forehead. If it didn't, then there was no point in going forward and developing a platform that would work from a hat. So let's have a bit of a discussion about how PPG sensors work. So a PPG sensor is essentially a sensor, and nowadays it's about the size of a grain of rice. They're very, very small, and it comes on a single chip, and it has LEDs in it. Now, the ones you're probably familiar with if you've ever gone to a hospital or doctor's surgery where they measure your heart rate and blood oxygen saturation, is it's normally attached to your finger. So I do have one, but I don't have it here. Oh, yes, I do. Perfect. All right, so let's go to the webcam. So normally you'll see a device such as this, and it will go onto your finger, and it's got LEDs inside it and a photo detector, and it will get your heart rate and blood oxygen level, which will be interesting to see what mine is. So I'll leave that on shortly and we'll come back to that. So essentially the LEDs emit light into the body, into the skin, and that light is either transmitted through the body in the case of where it's on your ear or sometimes on your finger, or in other cases it's reflected off internal parts of your body such as your bones and dispersed throughout the skin and comes back to a photodiode on the sensor. And it's not going to work, but I am at 97. My blood oxygen is at 97 and my heart rate's at 76, quite low. That's good. Not too low, but that's good. Back to PowerPoint. Okay, so basically it goes into the skin, it disperses through the skin, and it returns to the photodiode. So as the blood vessels, as your heart beats, the blood vessels engorge with blood and they absorb more of that light. And then as the pulse goes past that location, the blood vessels contract and they absorb less light. And this can be seen in a waveform with which we can calculate heart rate. But there's a few little things about color. So you'll notice on this we've got wavelengths, I should say. We've got 3 wavelengths of light. We've got infrared, red, and green. Now, you'll probably notice if you've got an Apple Watch or a Fitbit device or a Google Fitness watch that they have a green LED on the bottom of them. And there's a good reason for that. So as you can see here, green penetrates more shallowly into the skin. So it's a much shallow penetration into the skin, which means you get less movement artifacts from the sensor. Therefore, when it's on your wrists and you're running or jogging or swimming or whatever, you're not going to get as many movement artifacts, so it can detect the heart rate much more accurately. With red and infrared, they penetrate much deeper into the skin, therefore you can get more movement artifacts, and they're not as accurate when you're trying to move or when you're exercising. So that's why you see green on your watches. But you may ask yourself, why haven't most watch-based devices been able to do blood oxygen until now? Well, there's a very good reason for that. You can't get blood oxygen level using the green wavelength. You need red and infrared. So if we look at this graph down here, we can see oxyhemoglobin in red and deoxyhemoglobin in blue. So oxyhemoglobin is hemoglobin, which is it's a cell in your body, or part of your red blood cells, I should say, not a cell. It's part of your red blood cells in your body that carries oxygen around your body. Now, oxygen gets attached, and that changes the spectral properties of hemoglobin. As the oxygen detaches and goes into a muscle, for example, to be used, the hemoglobin becomes deoxyhemoglobin. It doesn't get carbon attached because carbon dioxide is mainly dissolved into the blood and then travels back to the lungs that way. So it becomes deoxyhemoglobin. So what we're measuring is a ratio between oxyhemoglobin and deoxyhemoglobin to find out how much oxygen is in your blood. So if we look at this graph, we can see that the spectral properties of oxyhemoglobin and deoxyhemoglobin at the green wavelength are pretty much the same. Whereas if we look at the red wavelength and the infrared wavelength, we can see that the spectral properties of both are different. So then we can use these properties of oxyhemoglobin and deoxyhemoglobin to calculate blood oxygen saturation. The other important thing we need to take into consideration with PPG sensors is penetration depth with regards to skin tone. The darker your skin tone, the shallower that the sensor will penetrate. Unfortunately, there's not much we can do about that. That's just the properties of light. So let's have a look at a PPG waveform. So in this example, I don't have green, I only have red and infrared, but green basically works on the same principles. What we can see is the heart rate is each of these bumps in the waveform. So each peak is a pulse, each valley is where it is in between pulses. By doing that, we can just use a simple time between pulses, as in this case, or we can count the number of pulses over time to calculate heart rate. In this example, the heart rate is 96 beats per minute. We can also see respiration rate from this one sensor. So there's several methods of getting respiration rate, and I won't go into them all. It's just simply not enough time today. But this is one method here, and the change in amplitude over time of the heartbeat represents the respiration rate. And that's got to do with changes in the pleural cavity due to breathing. There's other ways we can see that. So we can actually get respiration rate, heart rate, and blood oxygen out of this one signal source, or one waveform. And to get blood oxygen saturation, I won't go through the calculations because it's going to bore people, but essentially we're looking at a ratio between the red waveform and the infrared waveform, so the amplitude of that waveform at the same point in time. And that ratio tells us what the blood oxygen saturation is. So we wrote a paper on this. We did a study and we wrote a paper. So the paper was published in Sensors, an open source publication. So feel free to go and download that paper if you wish. And basically we made a device here, or we used off-the-shelf components. We had 8 PPG sensors connected to this device here, which allows us to all to connect into one microcontroller. And that means we could actually measure 8 locations at the same time, simultaneously. And therefore we can compare those locations because they're all done at the same time, we can make a good comparison of each of these locations with regards to collecting respiration, heart rate, and blood oxygen saturation. We had the sensors located on the forehead, the temple, the rib cage, the finger, the tibia, the lower back, the wrist, and the back of the neck. We also had the commercial sensor, which you saw earlier, this one, on the finger. And we use that as our ground truth for our blood oxygen and heart rate. We've also had a band on the chest that has been developed by my supervisor for, he's using that as in a shirt for measuring, for studies on sleep apnea, but you can measure respiration rate by changes in the size of the lungs. So that was our ground truth for respiration rate. As you can see in the hat, we actually had it sewed into the brim of the hat. We have a much better way of doing it now, but this is one of our first ways of doing it. It worked quite well. So this is some of the raw data. This is the finger pre-processed. This is after we process the data. You can see it's much cleaner, much easier to see. This is the forehead. Again, the forehead nice and clean. So these two happen to be our best locations. The finger doesn't surprise me, considering that's a commonly used location in healthcare. And the forehead, I was kind of expecting that to be a good location as well. However, the lower back and the rib cage were not great. They suffered from a lot of movement artifacts and didn't work quite so well. In fact, not very well at all. We also did tests while resting and also while walking, because we wanted to see the difference between each of these locations while we're at rest, so basically sitting in a seat, and while we're walking, because that was also important if we were going to have this device used on a day-to-day in usual activities. We wanted to make sure that it would continue to work while the participant was walking. And what we did find was that the finger was the best location overall, but the forehead was actually a good location as well. Surprisingly, in our study, the wrist wasn't a good location. And as I said before, when I was talking about the different colors of, or the different wavelengths of PPG, the reason we use green is it's a lot better. It doesn't penetrate as deeply into the skin, so it doesn't get affected by movement artifacts as much. These sensors we used in this test didn't have the green wavelength, they only had infrared and red. And as you can see, the wrist performed pretty poorly on those wavelengths. So we also did a second study where we did a comparison between a bi-wavelength, which is red and infrared sensor, and a tri-wavelength sensor, which is red, infrared, and green. And that one's published in the IEEE, so unfortunately it's not open source. You will need to access that through an institution or purchase that through IEEE. So in this instance, we had both sensors installed into the hat. And as you can see here, we've really upgraded the way we've done this compared to the first study. We've got a skin safe or biologically safe silicon, and we embedded the sensors in that silicon inside the hat. This served two purposes. It prevented light leakage from the outside world, and it also made it more comfortable for the participants in the study. As our ground truth, now we weren't doing walking in this study because we already confirmed that walking is successful in this location. It was only at rest. I used Lego, to mount a webcam, and that webcam basically recorded the finger-based PPG sensor, and using optical character recognition, I converted the values on that sensor into a CSV file, which then I could import into my software to do comparison between the two. So that was our ground truth, but I had it all automatically done, which made life a lot easier. What we can see down the bottom here is the two sensors. On the left, we can see the bi-wavelength sensor, and the right, we can see the tri-wavelength sensor. Now these boards are dev boards, development boards from the manufacturer, but the sensors here are essentially the same size for both types of sensors. And the nice thing about these, they've got analog to digital conversion on board, and they've also got something called I2C, which is a communication protocol built in on board. So it's really easy to interface with these devices. There's no worry about having to convert an analog to digital signal after the fact. Sorry, I've just spilled my drink. I apologize for that. So these sensors are quite good, and they've been pretty much validated at the factory to work well. What we can see here is our tri-wavelength sensor at the top. We can see our red, infrared, and green. And at the bottom, we can see our bi-wavelength sensor. We can see red and infrared. Now, this is, I can't remember, I think this is the raw signal actually, from memory. So you can see that the signal on the newer board, I should say that the tri-wavelength sensor is newer, is much cleaner than the bi-wavelength sensor. But they all work, they both worked really well, and they both were able to collect the data. But we did find that the tri-wavelength sensor was more accurate overall. So we've decided to go with that sensor in our platform. So let's have a look at the citizen science environmental stack, sensor stack. So I've basically created a Stevenson cage. I have a smaller version of this, which is 3D printed, and there's a reason I'm not using that anymore. And I'll talk about that in a second. And essentially inside this, I've got the environmental sensors that we mentioned before. So the citizen science environmental sensor stack, I think I need a better word for that because it's a mouthful, was developed initially to evaluate sensors for the WEBS platform. So while we're evaluating the biological sensors for the platform, we also wanted to evaluate the environmental sensors for the platform to make sure we selected the right sensors. The platform was deployed in a Western Sydney community for a year, and it was running during the entire 2019-2020 bushfire emergency, and it collected some interesting data. So it's capable of distinguishing between a smoke and dust related event, and it provides data at 5-second intervals. It shares the same base hardware of the WEBS platform, so it still has Bluetooth and Wi-Fi connections. It has an option for cellular data access, so we can put this in a remote location where there's cellular data and upload that and have that data come back to a central point. It has a micro SD card slot for local data storage, so if there's no data or communications options, we can store it locally. It can be powered from mains, battery, solar, or a solar/battery solution. And we've also got a mobile phone application which works with that as well. So it measures, it measures particulate matter, PM10, PM4, PM2.5, and PM1.0. Sorry, I'm just saving some devices from the water I spilt. I apologize. It's got gas sensors, nitrogen dioxide, but can be extended to measure other gases such as nitrogen dioxide, carbon dioxide, ozone, carbon monoxide, hydrogen sulfide, and sulfur dioxide. It also measures volatile organic compounds as well. It can measure temperature, pressure, relative humidity, and it's also modular. So we can add other sensors to it. For example, a rain gauge, anemometer, wind direction, UV index sensor, an ambient light sensor. It's really a very modular platform. We can really add a whole stack of different sensors to this. Before I go on, the reason we don't use the smaller Stevenson cage that I 3D printed anymore is the temperature was not reliable in that solution because it was so small. Also, they didn't have great thermal properties. So you'd notice as soon as the sun hit it, the temperature shot up. So we've had to move to a solution where we have a wooden enclosure, and that seems to be performing a bit better. Particulate matter is, I didn't talk about this. This slide's supposed to be earlier. Sorry about that. Particulate matter is measured in micrograms per meter cubed according to particulate size. A concentration value for PM10 is the concentration of particulates of 10 micrometers in diameter or smaller. Therefore, PM10 includes PM4, 2.5, and 1.0 values. PM4, therefore, is 4 micrometers or smaller, PM2.5, 2.5 micrometers or smaller, and so on. So it's important to understand that a PM concentration for particulate matter in PM includes everything below it. So a PM10 will also include PM2.5, PM4, and PM1. So therefore, PM4 should be lower than PM10 in all instances. So we've compared our citizen environmental stack. I'm going to try and speed up because we are running out of time, with the closest New South Wales Department of Planning Industry Environmental Quality Monitoring stations, which you can go to their website and check that out. At the top of the figure, we can see the air quality measurement index, and essentially that's a direct relationship with the particulate matter size. With regards to other gases, it's a bit different, but it's basically the highest value it's out of all of those metrics is recorded as the air quality index. I'm going to skip over that because we are running out of time. So let's have a look at some examples from the 2019-2020 bushfire season. So what we see here is in October 2019, we had the mid-north coast bushfires raging. And what we can see here is these lines in blue, red, yellow, and purple are from our monitoring station running in Western Sydney. And our monitoring station is about 3 kilometres from the St Mary's site. So St Mary's is the closest official monitoring station, which is why we've chosen that as a comparison. So what we can see here is this is a smoke event. So we can tell it's a smoke event because smoke tends to have finer particulate matter and tends to have ultrafine particulate matter smaller than 1.0 micrometers in diameter. So what we see in a smoke event is PM1, PM2.5, PM4, and PM10 are very close together. The concentration of those values is very close together because remember, PM10 includes everything below that as well. So this is a smoke event from the bushfires. But here, what we see is a dust storm event. And I can tell the difference because what we see is PM10 in purple has a much higher concentration than does the smaller particles such as PM1 in blue. And that's because dust from dust storms tends to be more coarse particles. So that's why you don't see the finer particles in there. And this is an easy way for us to distinguish between a smoke event and a dust event using our sensor. I apologise, that's not the Mid-North Coast bushfires, but it is in November. This is the Mid-North Coast bushfires, and this is an event that we saw towards the end of October. In this event, Sydney had some really bad air quality from those bushfires up the Mid-North Coast. The wind was blowing the air into the basin, it was congregating in the basin, and we had this visibility quite low in the Sydney Basin. And as we can see, the air quality index the air quality was rated as poor in the Sydney Basin. The other interesting thing about this plot is on this day, even there's a high correlation between the St Mary's, the official St Mary's site, and our data, which is 3 kilometres away. But I must say it's not always the case, and there's plenty of reasons why that may not always be the case. Here was one of the worst days we had in December. On this day, fires were raging in the south of Sydney, southwest of Sydney, I should say, and the Greenwater Creek fire was raging, and the Ruin Castle fire was raging in the Blue Mountains, which caused really bad air quality in Sydney. And we had levels which were hazardous on both of these days. On the 9th and 10th of December, it was well above hazardous, particularly on the 10th of December, where we had levels up to just under 1,100 micrograms per meter cubed for particulate matter we've got our sensor in Western Sydney. And again, we can see a very high correlation with the St Mary's sensor in light blue and green, pretty much almost exactly following the sensor we have here in Western Sydney, in our Western Sydney community. Now, this one is where we start to get a little interesting. We start to see some discrepancies with the official monitoring station. Again, this is in December. Again, we've got some poor air quality from bushfires. However, we're starting to see different spikes at the St Mary's location compared to our sensor stack. And it's important to remember that there's a 3 kilometre difference between our sensor location and the St Mary's location. And this could account for these discrepancies here. It could be a different wind direction. It could be blowing the smoke away from our sensors, meaning that the St Mary's location has a higher concentration than our sensor location. I would like to get our sensor put directly next to one of the official stations to have a much better comparison between our sensor and theirs. So that's something I'd like to do in the future. The other thing is we can also see another dust storm event here, 2 of them in fact, on the overnight of the December 16-17 and also the night of the 17-18. Almost there. So this is one in January. This has got some interesting things with the St Mary's station that I wanted to point out. For some reason, PM2.5 is lagging PM10, which I find odd. I'm not sure why the station is doing that. I just found that quite weird. Just something I wanted to point out there. That's it. So, sorry, it took a little bit longer than expected, but any questions?
Okay, thank you very much, Sally, for the great presentation. In fact, you're doing a great research. It's very interesting.
Thanks.
I quickly go through the questions. We have a question for you from Judith. Hi, Sally. It sounds like a really great project. It will be a lot of data processing. Is there any possibility of measuring ozone? Ambient ozone is very low concentration and maybe below detection. It would be very interesting to see if people immediately responded to ozone on high ozone days in summer.
That's an interesting question. And the answer to that is, well, we haven't tested the sensors for ozone, but because the platform's modular, there's no reason we couldn't add an ozone sensor to that platform. So we could add an ozone sensor to the hat, for example, to measure more direct ozone layers or ozone concentrations with the person wearing the hat or the participant. Or we can also add it to the environmental monitor as well. So while we don't have it at the moment, there's no reason we couldn't add that sensor on. As to how sensitive those sensors are, I don't know. I haven't actually assessed or evaluated those sensors at this point in time. But it's interesting. I would like to do that, actually.
Okay, good, thank you.
Thank you.
Is there any other questions here? If not, yes, Michael, please.
Hi, Sally. Can
Hi,
you
Michael.
hear me okay?
Yes, I can hear you.
It's really cool technology you've developed. I think many of us would be quite keen to use it. Just
Thank
with
you.
your final set of results, I understand that ultrafine particles can aggregate in transit, which is why you can sometimes have quite high levels of PM10 from a bushfire, which is, you know, some distance away from the city where the monitors are, and not very high levels of ultrafines. I just wondered whether similar things have been observed with PM2.5 or not.
I'm not, I mean, the thing with my understanding anyway, I could be wrong in my understanding, is that measurements of PM10 should also include PM2.5, because PM10, the definition of PM10 is particulates less than 10 micrometers in size, whereas PM2.5 is less than 2.5 micrometers in size. So it should include that value. But I do get what you're saying there. If they are congregating or if they are clumping together in the air, then that's actually an interesting question. I mean, the good thing, what I'm thinking of here is, would the detector detect that clump as a larger size than it really is? That's another thing I'm thinking. So,
well, it might not go through the size selective inlet, whereas
right.
I think your technology is different.
Yeah, it is. It's not a selective inlet. It's measuring using a laser to measure all of the particulates that come through. So, yeah, I'm not 100% certain. Sorry, but it'd be interesting to see. What I'd really like to do is have the sensors side by side with one of the stations and see what the correlation is there. I'm not sure if I answered your question or not. I'm sorry.
Okay, thank you. So we have another question from Leon. Thank you for the wonderful talk.
Yeah.
For one day with a better personalized sensor, do you see over or underestimation of exposure if environmental monitoring is used?
Sorry, could you repeat that?
Let me restate the question.
Yeah,
so
sure.
Usually when we measure the outcome, for example, lung function,
Yep.
blood pressure, or those more clinical outcomes, it cannot be so discrete as to minute by minute or second by second.
Yep.
So one day is probably the minimal resolution that we are doing. So I think if you accumulate one day or a week or a month, do you see overall overestimation or underestimation by using the environmental data as compared to your more accurate sensory?
Okay, so just so I can understand your question, are you saying that the pollutants would like build up over time?
No, no. In here you show both the sensor data, the more accurate sensor, but you also show St. Mary's PM
right.
2.5.
Yep.
Sometimes it's higher, sometimes lower.
Yep.
But if you accumulate the whole day or the whole week, do you see over or underestimate if you use the environmental monitoring?
That's a very good point. It's not something I've looked at just yet. Unfortunately, I've only really been looking at this data for the last few weeks. I haven't had much of a chance at the beginning of the year. I was writing some papers. But I guess one thing I forgot to point out is the St. Mary's data isn't average over the past hour, whereas our data isn't. So that's something I need to do is average our data out over an hour and see if that correlates better. But it's a very good point, and I should see what the averages are over a longer period of time. And that's something I will do, and I'm happy to share that with you if you want.
That would be wonderful. Thank you. Look forward to it. Thank you, and congratulations.
Thank
for
you.
A nice talk.
Thank you.
Okay, thank you very, very much. I also have one question. My question is about environmental parameters, and it's about wind speed. I'm wondering, do you consider wind speed as well in your measurements? Because you talked about wind direction, but what about wind speed?
We're not at this point in time. It's something I'd like to add to the environmental monitor, the stationary monitor, is wind speed and wind direction, because I think that's an important thing to measure, is particularly, you know, some of the discrepancies between our station and St. Mary's could be because of wind speed and direction. So I don't have that data at the moment. I'd like to add that. With regards to the WEBS platform, the wearable version of it, I don't think wind speed and direction's such a is something that we need to measure, because we're measuring basically on the side of the head, so really close to the mouth. So essentially we're at the same height as the mouth as well, pretty much, or maybe a few centimeters higher, but pretty close to it. So I think we're going to get very similar metrics compared to what the test subject would have. So I don't think it's necessary to measure it in that sort of scenario. And I think it'd be difficult for them to walk around with an enometer and that on their head. But certainly on the environmental platform that we're talking about, the stationary platform, I would love to add that.
Good, thank you. Is there any other questions for Sally today?
Additional question, please.
Yes.
So how expensive is per person monitoring?
At the moment, because we're sort of making them on a one-by-one basis, they're relatively expensive. You're probably looking about $700 per hat. But you know, if we were to scale this up, we could certainly bring those costs down to maybe $200 or $300 a hat. It's just at the moment, it's all being manually created pretty much. We did get the circuit boards created in China, and we have them now. But yeah, the higher volume, the cheaper it will get.
Okay, good. Thank you. Thank you very much, Sally, for your great talk. And thank you, everyone, for joining us today. Here we close the session and hope to see you later. Thank you. Bye.
Thank you, everybody. Thank you.